The stirrup, shown here, will tap, tap, tap onto the oval window here and create vibrations in this liquid, this fluid here called perilymph that's inside the cochlea. And those vibrations that are being transmitted through that fluid will end up moving this basilar membrane. And the basilar membrane is not perfectly even, so it has kind of an angular shape. And because of the shape and differences in thickness, note it's a little thicker here at the base and a little bit thinner here at the far end called the apex. So the area right by the stirrup is the base, and then the far end of the basilar membrane is the apex. And again, because of the variations in its shape and thickness, it will respond to low frequency sound waves over here on the far end of the apex, and high frequency sound waves more over here on the base side of things. Here we can really see, if you look at the basilar membrane, hey, yeah, so a really low frequency sound of 20 hertz will produce a reaction on hair cells that are way out here on the apex side. Now 100 hertz, a little more in, 1,000 hertz more towards the middle, 10,000 and 20,000. So the 20,000, the very high frequency set of sounds, are creating movements of the hair cells, those auditory receptors, closest here to the base. And this range pretty much is the range of human hearing. So humans can generally hear from 20 hertz to 20,000 hertz. And so that's basically what we're seeing here. Here on the bottom, we're really just noticing that, like, for example, here where it says 10,000 as an example, well, it doesn't mean that it will ignore a frequency of 10,500. What we see here is that it will react to a range of sounds, but it'll have the biggest response at 10,000 and a smaller response at 10,500, for example, or 9,500. But we're seeing sort of a maximum at that peak response area. If we take a close look at the basilar membrane, you can see now oh my gosh, look at these hair cells, right? So we can see the hair cells, they have cilia, and they're sort of shearing motions between the basilar membrane and then this tectorial membrane that's above it, and that creates a lot of friction, which ends up moving the hair cells. Now there are inner hair cells and outer hair cells. They're both important. The outer hair cells help to refine our reactions to sounds, but the inner hair cells are the actual receptors. The inner hair cells create a neural signal depending on which way they bend, interestingly enough. So if they bend one way, we get depolarization of the hair cells. If you remember, depolarization means the hair cell, that neuron, will become more excited, more positive, and that'll lead to more neurotransmitter being released. But then when they bend back and go the opposite direction, they will become hyperpolarized, or they will become more negative. Imagine seaweed in the ocean, and a wave comes by, and the seaweed's going to move first, for example, to the right, and during that time, it might be, the hair cell might be releasing a lot of neurotransmitter because it's super excited. And then as the wave passes, the seaweed will shift over and now bend the opposite direction to the left. And when it does this, the hair cell actually becomes inhibited. And so we get a repeating pattern of excitation and inhibition as the sound waves go through the basilar membrane. Now, auditory hair cells are super amazing. They are super fast. They allow us to detect differences in the time of arrival of a sound that are 10 millionth of a second. That is amazing. And that allows the left ear and the right ear to detect tiny differences in the time it takes a sound to hit our ears. And obviously, if it hits our right ear a little bit faster, it's because the sound is a little bit closer to the right side, and it helps us locate a sound and distinguish between a sound to our right versus a sound to our left. So they are amazingly precise because of that. And they can create a neural signal from a really tiny deflection of just 1 nanometer. Super sensitive. So we don't want to injure them either, right? Now let's take a look at how these different sounds stimulate hair cells in different regions of the basilar membrane, and how it kind of would work for a more complex sound. So remember, low frequency stimulate hair cells out here at the apex. high frequency stimulate hair cells over here at the base. Going in. There's the cochlea. And we're just going to unwind it. And there's the basilar membrane. So low, medium, high frequencies.